So what we're doing in this, we've been working with trig functions for a while and using them sort of in discrete ways to like solve problems, like solve triangles or maybe work with vectors. What we're going to do now is examine these functions graphically. We're going to basically spend a little bit of time figuring out what the graphs of sine x and cosine x look like, and then use that and make some observations about how we might change, how changes in the equations themselves will result in changes in what the function, the graph of the function looks like. So we could develop a kind of procedure to tackle how to solve or how to graph maybe more complicated trig functions. So we're going to begin by plotting a bunch of points to sketch out a graph. I mean, we know that one way we can graph a function is to just put in some x values, see what the y values get out. You get a bunch of coordinates, right, in the plane, and then you connect them with like a smooth curve. So we're going to start out doing that just for a couple of graphs. And then if we do our jobs well, we won't have to go through this much for other functions, more complicated functions, right? So we're putting in a lot of the legwork right now for some simple functions. So we're going to start with the sine function. I've got a handy-dandy unit circle here in our notes. And what we're going to do is use the unit circle to help us fill in these values. Now, generally, unless stated otherwise, our angles are always going to be in radians. So that's why we have like pi over 4 instead of 45 degrees here. So if I want sine of 0, first of all, how do we use the unit circle to get the values of sine? What is it that I'm looking for? What's that? A y coordinate. So at 0 radians, we're down here, and the y coordinate is 0, which means minus sine of 0 is also 0. At pi over 4, what is the y coordinate? Yep, root 2 over 2. And so negative sine of pi over 4 is a minus root 2 over 2. Let's keep going. At pi over 2 is up here at the top of the circle. So there the y coordinate is 1, which means that minus sine of pi over 2 is a negative 1. What about 3 pi over 4?
Root 2 over 2.
Root 2 over 2. So over here it would be a negative root 2 over 2. Sine of pi? 0. And so that negative sine of pi is also 0. 5 pi over 4.
Negative root 2 over 2.
Negative root 2 over 2. And so negative sine of 5 pi over
3 pi over 4, is that reversed?
3 pi over 4 sine is a positive root 2 over 2. And so negative sine is a negative root 2 over 2. Yeah. Yes. Does that answer your question? I don't know if you answered it. No?
Not really. It seems like it's the same as pi over 4.
Yeah, it is the same as pi over 4. Like, so at pi over 4 and 3 pi over 4. So here's pi over 4, right? With those coordinates. And here's 3 pi over 4 with these coordinates. Sine is the same, right? The y coordinate is the same. we're only tracking the y-coordinate. It's not like we're doing x, it's not like we're doing sine and then cosine. What we're doing is sine and then minus sine. So we actually don't care at all about the x coordinates in this. Does that help?
Yeah.
Okay. So at 5 pi over 4 minus sine of x is a positive root 2 over 2. 3 pi over 2 are at the bottom of the circle, so sine is a negative 1, which means the negative sine x there is going to be a positive 1. And 7 pi over 4, we're over here in the fourth quadrant. Sine is a negative root 2 over 2, so its negative is a positive root 2 over 2. And then at 2 pi, we're back at the same as 0. 2 pi and 0 are the same angle, basically, so they're both 0 there. So I basically just picked these values at the quarters, right? Like these halfway through each quadrant. We could, if we wanted to, try to plot more points, included the individual, the in-between angles like pi over 6 and pi over 3 and all the way, but I figured like this is sort of enough for us to get an idea of what it looks like. So now what we're going to do is sketch. Notice, of course, and we've known this for a while, of course, these values of sine and minus sine are always in between, 1 and negative 1. So my y-coordinates don't need to extend beyond positive 1. And they don't have to extend beyond negative 1. Right, so I know the outputs will always be in between these values. Also, I only really have to consider one go around the circle. You know, I stopped at 2 pi. And and the reason I did that is because if, let's say I went further, like 2 pi plus pi over 4 is 9 pi over 4. Let's say I did 9 pi over 4. Well, that would just put me back here, right? Like the cycle starts again. So there's not much point in going beyond one full revolution. So that means my inputs really only need to go out to 2 pi. And then I'm going to break this up into each of these. Whoops. So this will be pi. Halfway would be pi. And then we have pi over 2. This would be 3 pi over 2. So there it is in quarters. And then I actually want to split them up into halves again so I can have those pi over 4 units. So I've got pi over 4, pi over 2, 3 pi over 4. 5 pi over 4, and then this would be 7 pi over 4. And now I'm going to begin by plotting out the positive sine x. So at 0, sine is 0. I'm just really taking these values from the table. And so, well, since we're going to plot these, maybe we'll get an approximation. Root 2 over 2 should give us 0.707. And likewise, negative 0.707 for those negative values. So that's probably about here. So at pi over 4, we're up here. Then at, pi over 4, root 2 over 2, pi over 2, we're up there at 1. At 3 pi over 4, sine is back down to root 2 over 2. And at pi, we're at 0. At 5 pi over 4, we're down to negative root 2 over 2. At 3 pi over 2, we're at the bottom of the circle, so that's negative 1. At 7 pi over 4, we're at negative root 2 over 2. And at 2 pi, we're back to 0. And if we connect these dots with a smooth curve, it'll look something like this. So here's our y equals sine x. And I know if I wanted to graph it beyond 2 pi, I know exactly what it would look like. It would just be the same kind of waveform repeating itself, right? Because it's just another go around the circle. Before we move on, we'll do one more here because we did plot those, or we did figure out the coordinates for the minus sine x. So if we graph the minus sine x, just taking the values in this second column that we plotted, it would look like at pi over 4, negative root 2 over 2. Then at pi over 2 would be at negative 1. And at 3 pi over 4, negative root 2 over 2. I'm just taking each of those values we found and plotting the point that goes with it. At 3 pi over 2 would be a positive 1. 7 pi over 4, we're down to root 2 over 2. And then at 2 pi, we're at 0. And so negative sine x looks kind of like this. These graphs are very closely related to each other. In fact, really, to describe mathematically what one graph is of the others, we'd say it's just a reflection. We just flipped it over. It's reflected about the x-axis. And that is generally true if you compare the graph of y equals f of x for any function and y equals negative of f of x. You just sort of flip everything over the x-axis. So essentially what we're doing when we're graphing the sine function is we're saying we're picturing this unit circle as though it were like a wheel able to spin around. And if I sort of distinguish one point as special, right, like this one right here, and then as this wheel turns around, what this is doing is just keeping track of what the x coordinates are. So we could see that as this moves up counterclockwise, it should start by rising, cresting at 1, and then it falls again until it goes down to negative 1. It looks like this. Oops. Kind of like that. So you can sort of see that point moving around. Why is it do that point moving around the circle and how it corresponds to the y coordinate on the graph. That's essentially what we're doing. Let's do another one. This time, let's work with the cosine. We're going to do it with the same set of values, right? So we're going to stop and look at what happens at the pi over 4, the 0, the pi over 4, the pi over 2, and so on down the list. Cosine, though, we're looking for the x coordinates. So at 0, what is cosine of 0? Nope. 1, because it's the x coordinates this time, right? So there's 0. We want the x coordinates. So this would be 1. So negative cosine of 0 would be negative 1. What are we doing at pi over 4? What's cosine? Root 2 over 2, or about 0.707. And so negative cosine of pi over 4 would be negative root 2 over 2. I'm just taking the negative of that value to put in the third column there. At pi over 2, that's the top of the circle. What's cosine equal to? 0. And so its negative is still 0. How about 3 pi over 4 over in the second quadrant here? Negative root 2 over 2. And its negative is a positive root 2 over 2. How about at pi? Negative 1, and so its negative is a positive 1. At 5 pi over 4?
Negative root 2 over 2.
Negative root 2 over 2. Its negative in the other column is a positive root 2 over 2. 3 pi over 2, that's at the bottom.
0.
0, and its negative is 0. 7 pi over 4?
Root 2 over 2.
Root 2 over 2, and its negative is a negative root 2 over 2. And 2 pi? 1 and negative 1. Great. So we're going to do the same thing now, and we're going to sketch a graph of cosine x and negative cosine x. And, cosine is bound by those same values, negative 1 and 1, just by the nature of the unit circle. It's something that we've known for a while now. But it means that my y coordinates need not extend beyond 1 or down past negative 1. And we're going to cut up this interval from 0 to 2 pi into these subintervals, just like we did last time. So halfway is pi, that must be pi over 2. This would be 3 pi over 2. And then we have the pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Let's plot some points. At 0, the cosine function is 1, so I'm going to plot the positive cosine function first. At pi over 4, we were at root 2 over 2. So that would be down here. At pi over 2, we're at 0. At 3 pi over 4, we're at negative root 2 over 2, and at pi, we're at negative 1. At 5 pi over 4, back to negative root 2 over 2. At 3 pi over 2, we're at 0. That's the bottom of the circle. And at 7 pi over 4, we're at root 2 over 2. And at 2 pi, we're back at positive 1. Just taking these values we put in that middle column that we filled in up above. Now, if we were to draw a smooth curve to fit these, it would look something like this. Now, basically, it looks different, but it basically has the same shape. Because if I were to continue this curve, it would look like, it would just sort of keep going, and you could sort of see that same, just like a sine curve, the one that we graphed on the last page. We don't go any further than just 0 to 2 pi because, of course, we know that the values just repeat themselves. So that's why we say, well, we only really need to, cosine is defined for all real numbers, right? We could plug in any angle, but there's no need to graph beyond 0 to 2 pi in this case just because it repeats itself after that point. Now, if we were to plot the other column, the last column we filled in for negative cosine x, that one starts out at 0 is negative 1. At pi over 4, we're at negative root 2 over 2. The same thing will happen, right? This will just be a reflection of the graph we just, flipping it over the x-axis. It looks like this. So this one is y equals negative cosine x, and the one in black that we did first is y equals positive cosine x. These are the basic shape for the sine and the cosine functions. Even if we make changes, and we're about to sort of examine what kinds of changes in the equations can have on the effect of the graph, the same basic shape will be retained, right? So we're going to learn how we make adjustments. And essentially how we can plot any number of sine cosine curves while making sure we only need to plot a very minimum number of points, right? So because we don't have to keep going through this process of making a little table every time we want to see what this graph looks like. Sort of illustrate the cosine. Now the cosine is the x-coordinate. So as we start this kind of animation here, you're going to see the x-coordinate traced down here, and then they kind of translate it into the y, because when we graph a function, we always graph the outputs on the y and the inputs on the x. So that's essentially the same thing, kind of imagining us being able to spin the unit circle as like a bicycle wheel, being able to spin that around and then tracking what's happening to the x-coordinates at those points as we spin the wheel around. How are we doing so far? All right. All right. Okay, so now one of the changes we can make is to what we call the amplitude of the graph, and we're going to sort of illustrate that by, yes, filling in another table, but way fewer way fewer angles, right? So just sort of cut it down to like the extremes on the circle. So 0 pi over 2 pi and 3 pi over 2 and 2 pi. So if we track 2 times sine of x, so just take the y coordinate and double it on the unit circle. That's what we want to do. As 0, 2 times 0 is 0. At pi over 2, that's the top of the circle, so sine is equal to 1, and double that, we get 2. At pi, the y coordinate is 0 again, so double that, and we get 0. At 3 pi over 2, we're at negative 1, so double that, we get negative 2. And at 2 pi, that's back at 0 again, we double that, we get 0. What do you think we're going to get for 1/2 sine of x? Who wants to fill in these values?
0. 1?
Nope. 1/2. Because we're taking half of the original sine, not half of the other column. Yep. So 1/2, and then 0, negative 1/2, and 0 again. Okay. So we're going to graph both of these. Now this time, I'm looking at the outputs I get for these. I have to go as far up as 2 and as far down as negative 2. So I'm going to graph the 2 times sine x first. Going out to 2 pi, and I'm going by pi over 2. So pi over 2 pi, 3 pi over 2, 2 pi. So the sine 2x is at 0, then we're up at 2, and we're down at 0, down at negative 2, and then at 2 pi. It'll look like this. Now I'm just filling in the shape, because I know what the shape looks like. I'm just going to fill it in there. And here's something that's pretty important when you're graphing these. We're graphing a smooth curve. If you're plotting a point like, plotting points like this, and usually we can graph any sine or cosine by plotting just 4 points like I did, right? We don't have to fill in a lot more because we know how to fill in a smooth curve. But when you do that, your graph definitely should not look like that. Okay? It is a smooth curve, so don't make it look like Charlie Brown's t-shirt. So boy, this was remarkably similar to just graphing the sine function, right? In fact, it's almost like we just took that sine function that we did graph and replaced the 1 and the negative 1 with a 2 and a negative 2. And that is essentially all we needed to do. Let's graph the other one on the same set of axes here. This one now was 1/2 sine x. That only goes up as far as 1/2 and as far down as negative 1/2. So I'm plotting those out. Make sure I get the scales about right. And I'll plot this one in blue, I guess. So this was at 0, this is at 1/2, 0, negative 1/2, 0. Same shape, but that number out in front seems to just dictate how far we kind of stray from the x-axis, what I might kind of call like the equilibrium of the graph itself. The same basic shape is retained, though, in the graph. I mean, we could look at that and say, I know it's a sine graph. Okay. This measure of how far we stray from the 0, from the x-axis, we call that the amplitude of the graph. And so if we're graphing something that looks like a times sine x or a times cosine x, right? So just the sine or the cosine graph, but I've got a number out in front. That number out in front, the absolute value of that number is the amplitude. The amplitude is always just how far it's straight. It's always a positive. If it's a negative number in front, that just means that it's also reflected across the graph. But for example, the amplitude of sine 2x is 2, but the amplitude of negative 2 sine x is also 2. Right? The fact that that's a negative 2 out in front doesn't change what the amplitude is. We will see that in the graph because it'll be reflected across the x-axis as compared to the graph of 2 sine x. Let's do another example. Let's say we want to sketch the graph of y equals -3 cosine x. Now, I didn't even make a table here for us this time, and I don't think we're going to need one. Here's what we're going to kind of want to observe. For starters, that this amplitude, what's the amplitude for this function? Yeah. So the amplitude is 3. If the amplitude is 3, here's how that is reflected in my graph. When I mark off how far I need to stray from the 0, it's going to go up to 3 and down to -3. And this is a negative here, so that means it's reflected. And it's a cosine, so I'm going to start with a basic cosine shape. I'm still just graphing from 0 to 2 pi, so I've got to mark those out on my x-axis and cut that up into quarters, like we've been doing. So that's a pi over 2, and 3 pi over 2. Now the cosine graph, let's sort of review that again. The cosine graph is the one that starts at the extreme, and negative cosine starts at the bottom extreme. So when we're graphing -3 cosine of x, that means that our first point is going to start down at -3. And from there, the rest of it is sort of determined. At pi over 2, we're going to be at 0. At pi, we're going to be up at +3 at 3 pi over 2, back to 0, and at 2 pi down to -3. And here's my cosine curve. So I'm paying attention to the fact that it's cosine shape I need to work with and not the sine shape. I mean, they're essentially the same shape, but they start at different places, right? So it's a negative cosine, which means I'm starting at -3 and not +3. The amplitude was 3, so that marked the extremes I needed to mark off on the y-axis. Very little difference between graphing this and just graphing cosine x or graphing negative cosine x. It just changes, you know, what values I'm marking off on the axes. Okay. Questions before we talk about period? Okay. These functions are called periodic because they repeat themselves. It's the same set of values. Like, we only graph from 0 to 2 pi because we know we're going to see exactly the same thing, the same shape repeated over and over again. That's what it means to be a periodic function. And we would say that this function and the sine function has a period length of 2 pi. Like when we said, oh, we only need to make one go around the circle because it's at that point that it just starts repeating again. That's the period length. So the kind of intuitive definition for the period of a function is how long it takes, or the interval length, for the function to start repeating itself. Another way to define it, and maybe a more rigorous way to define it, would be the distance or the length for the same respective place in the wave, right? So like here's its trough is at -3, and this is how long it takes to hit that trough again, right? The same place in the wave. Okay, now what we're going to do is see, so regular sine x and cosine x, and in fact any constant a times sine x or any constant a times cosine x, they all have the same period. It's all 2 pi. So now we're going to look at how we make this a little bit more interesting. And the way that we see changes in the period of a sine or cosine function in the equation itself is by multiplying the argument inside the function by a number. So we're looking at a times sine of bx. It's this value here. That's how I know. That's what I look to detect a change in period. And if we're multiplying that value, or if we're multiplying the argument by b, its period is 2 pi over b. So now that we're keeping track of not just amplitude but also period, time for a little bit of a procedure. So when you're given the function in the form of an equation, find the amplitude, find the period, Then you want to split up that period into fourths, mark that along the x-axis, mark your amplitude plus and minus on the y-axis, and then sketch whatever the shape is. So whether it's a sine curve that starts at 0 or a cosine that starts at one of the extremes. So we're going to graph sine 2x and sine x on the same set of axes. Now, sine 2x what is its amplitude? No. 1, because it's 1 sine of 2x. It's the number in front. And its period? Nope. That's what we look for, right? We're definitely looking to the 2. We know that's what makes it a change. But the period is 2 pi divided by this number, 2 pi over 2. So its period is just pi. In essence, when we see sine of 2x, that multiplier inside the sine function says, if we kind of bring it back to thinking about the unit circle as like a wheel that spins around, that says spin it around twice as fast. And if you do that, it will take half as long to complete a full period. That's why the period here is pi and not 2 pi, right? It's exactly half of what the period of sine x is. And for y equals sine x, the amplitude, of course, is 1, and the period is 2 pi. Because we're graphing these on the same set of axes, I wanted to mark these out first, get both of them figured out first, because I know that even though the period of sine 2x is pi, I got to go all the way up to 2 pi in order to accommodate the graph of y equals sine x. So if we just graph regular old y equals sine x first, we'll get that out of the way. Sine x starts where? At 0 or 1? 0. And does it go up or down from there? Up. So it starts at 0, goes up. Now the rest of its path is pretty much determined. At pi, we're back to 0. At 3 pi over 2, we're at -1. And at 2 pi, we're at 0. So here's our regular old sine of x. Now let's graph the sine of 2x. That has a period length of pi, so we got to cut that up into fourths. So there's pi over 2, so this would be pi over 4, and this would be 3 pi over 4. And while we're at it, I may as well include the other ones. This would be 5 pi over 4, 7 pi over 4. Now, sine of 2x, it's a positive sign, so I know that sine starts at 0. It's a positive sign, so it starts at 0, goes up. It's going to have the same kind of pattern of values, but, yeah, 3 pi over 4, and at pi. So here's one period length of sine of 2x. And if we're graphing them on the same set of axes, we could go ahead and just include the rest of these and graph 2 full period lengths. It would look something like this. It's going twice as fast. I've got 2 full periods fit into the same length that it takes 1 period of the sine of x. How's that? Okay. Yay. Okay. It's a good thing we're all feeling refreshed back from a break, ready to take on this graphing. Excited about it. All right, let's do another. We're going to sketch a couple cosine graphs. One of them is just the regular old y equals cosine x. So we know that this one has an amplitude of what? 1. And what's its period? Two pi. Yep. And then cosine for y equals cosine x over 2. What's its amplitude? Still 1. And its period, now we have to be careful. Cosine of x over 2 is the same as cosine of 1/2 x, right? X over 2 is the same as 1/2 x. So that means that the value of b, when we think about cosine bx, b is equal to 1/2. So when we find the period, this is 2 pi divided by 1/2. 2 pi divided by 1/2 is the same as 2 pi times 2, or 4 pi. So that's a long period. If we're thinking back to this concept of spinning the wheel around, finding cosine of 1/2 x, or x over 2, just says spin that wheel around half as fast as normal. It should take twice as long to finish. And that's why the period is twice as long as it is for cosine x. So I need my period on the x-axis has to accommodate the longest period. Of course, they both have an amplitude of 1, so that's easy. But I have to go as far out as 4 pi. Cutting this up into fourths. Now the cosine x has a period of 2 pi, so I need to also cut that up into fourths. So this would be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All right, so let's graph the regular old cosine x first. Where does cosine start? Up at 1, yeah, at the crest. And so then at pi over 2, it's at 0. Then at pi, we're at -1. At 3 pi over 2, we're at 0 again. And at 2 pi, we're at 1. So there's our cosine of x. Then cosine of x over 2, I'll do that one in blue. It still starts, it's a positive cosine of x over 2, so it still starts at +1. But let's see, its period was 4 pi, so that means that it's not until we get to pi that it gets to 0. Then at the halfway mark, we're down at the bottom. At 3 pi, we're at 0, and at 4 pi, we're back to the top. How we doing?
Peachy.
Peachy. Okay. Ready for another? Let's graph -2 sine of 3 pi x. So let's mark down our important information. What's the amplitude? 2. And what about the period?
-2?
Nope.
Just 2?
Nope. What is that? Say that again. How do you get 3 over 2?
You take this in the parentheses and divide by 2.
Not quite. What we do is we take 2 pi and divide it by the coefficient of x. So it's 2/3 actually, not 3/2. So this period is always 2 pi over b, and where b is the coefficient on x inside the function. So we get 2/3 for the period. So the amplitude is 2, so it goes far up as 2, as far down as -2. The period is 2/3, so I go to the end, I call that 2/3. Now I got to cut this up into fourths. So halfway to 2/3 is definitely 1/3. What's halfway to 1/3? 1/6. And now we got to figure out what is this guy. It's the third one. And that's always the trickiest one, but there's a simple way to do it. If we cut it up into fourths, then here's what we got. This is 1/6, 2/6, 3/6, 4/6. So that's 3/6 or 1/2. Once we've set up our x-axis, we've cut up our period into fourths, and we've marked our amplitude. I mean, at that point, we just sort of fill in the dots, so to speak. It's a sine function, so I know sine starts at 0. This is a negative sign, which means where does it go from here?
Down.
Down. So at the first quarter mark, we're at the negative extreme, then we're back to 0, then we're at the positive extreme, and then back to 0. Questions? Okay. All right, so we probably get a little bored just playing around with amplitude and period, so let's do phase shifting. A phase shift is nothing different than just a horizontal shift of a graph, but when we talk about periodic functions, we call them phase shifts instead of horizontal shifts. So we're going to look at how we can graph things, functions that look like a times bx plus c, or a times cosine of bx plus c. It's this plus c part here, inside the parentheses, that tells us we're going to have a phase shift. We have to be careful because that value c is not the phase shift itself. We have a little bit of work to do to figure out what that shift is going to be, but it's how we know there will be one. So, if you like to think of it in terms of just remembering a rule, if the graph is a times bx plus c, then that phase shift is just c over b units, and it goes to the left if it's positive, it goes to the right if it's negative. What I always do is just start out by factoring out this b, because whenever you have the x plus or minus some number by itself in parentheses, that's when you get to say, that's my phase shift right there. So as long as we start by factoring out that coefficient on x inside the function, then at that point we can just pluck out what the phase shift is. The one thing we got to remember is that if it's a plus, it actually gets shifted negative, which feels backwards, and if we're subtracting, it gets shifted in the positive direction, which feels a little bit backwards. But let's try one. So we're going to start out. We're going to graph the function 1/2 sine of x plus pi over 4. This 1/2 in the front, of course, that's the amplitude, so it has an amplitude of 1/2. The period, I'm still looking at the coefficient on x to help me find the period. So what should be the period for this function? 2 pi. Because it's just the coefficient on x is just 1, right? So it's 2 pi over 1, which is 2 pi. And it's x plus pi over 4. So x plus pi over 4 is already, the coefficient on x is already just 1 inside that function, which means that pi over 4 is our phase shift. We just need to also include the direction. It's a plus pi over 4, which means we're going to go to the left. Now, when I graph these functions with phase shifts, I usually do it in a couple of steps. I first graph the function without the phase shift. So we get 1/2 minus 1/2. The period is 2 pi, so I'm just, starting out the way I normally do. Now this phase shift is going to be to the left, so I didn't have to worry about allowing myself extra room. If the phase shift was to the right, I'd want to make sure I stopped the period a little bit to the left of that so I could make sure there's room to move the graph. So we're first going to just graph 1/2 sine of x and forget about the phase shift for a second. So the sine starts at 0. This is a positive sign, so it goes up from there. So there's the graph without the phase shift. Now what I need to do is make room or make the adjustment so I can slide this over by pi over 4 units. And when I do that, I got to make sure that I am accommodating it, that it fits in with the general scale. So like if this is pi over 2, pi over 4 is this distance here. Right? It's halfway to pi over 2, pi over 4. So since I'm going to the left, I need to include this negative pi over 4. Here's 3 pi over 4. Here's 5 pi over 4. 7 pi over 4. So now each one of these, what I generally kind of refer to these as my anchor points in the graph, you know, just those very few points that I actually plot to help me put the curve down. Each one of these anchor points, I'm just going to slide over pi over 4 units to left. So that goes over pi over 4. This goes over pi over 4. And I've made sure that I've actually made space so I know where each point should go. I didn't just sort of eyeball and say, oh, okay, I'm just going to draw the curve a little bit to the left. I've actually plotted in the x coordinate on the x-axis the x values for each of these points that I should have. And now here's my curve. So this guy right here is 1/2 sine of x plus pi over 4. Pretty. You guys gonna make it? Maybe. Can't you not wait to do some sketching on our quiz on Wednesday?
I'm so excited.
Good.
He thinks this is boring.
Andrew, I'm so disappointed. Alex just told on you.
I'm just shocked.
I know. I feel your pain. All right, let's do another one. This one's slightly less boring, I hope, for Andrew's sake. Hopefully, we'll see. Now, what makes this one a little different than the last one?
The shift is negative.
That's true. So there's one thing that makes it different.
1/2 before.
Yeah, we have a coefficient on x that's not 1, right? So the first thing I'm going to do is actually rewrite this function. I'm going to do it down here where I have a little bit more space. So they gave us -3 cosine of 1/2 x minus pi over 8. Okay. So what I want to do is rewrite this where by factoring out the 1/2 from the argument, it still remains inside the cosine. Like I can't pull anything outside of the cosine function. That definitely is not kosher. But I could certainly factor within this expression as long as it all stays in the argument. So that's what I want to do. Now if I factor out the 1/2, definitely my very first term has to be x, right? Nope. Pi over 4, yeah. Because if I were to distribute the 1/2 through, then this would be 1/2 times pi over 4, which is pi over 8. So now that I've factored it out, as long as I've done my factoring correctly, now it's this guy right here, this pi over 4. There's my phase shift. As long as it's what appears in the parentheses with just one x by itself. That's how I know. So we can't just say, oh, I'm subtracting, I know there's a phase shift, it must be pi over 8. You gotta make sure you do this factoring first, and then you can say point to the phase shift. And it is a phase shift in which direction? Pi over 4 to the right. Okay, so there's that part. What about the amplitude? 3. And the period? Let's say that again. And how do we get 4 pi?
Because we're
2 pi over 1/2.
Yeah, 2 pi divided by half is 4 pi.
you're halfway there.
Yeah, halfway there. Yep. It's my job to push you to strive to explain it, though.
Someday.
All right, so we have all the important information. We know that there's going to be a reflection because it's a negative cosine, and that it's a cosine curve, so it starts at the extreme. So what do we do next? I mean, here we just have some empty axes. So plot out the 3, so that's at the top and the bottom here. So that's as far as we go in the up or down direction.
Gonna have to put 4 pi inward. Because you gotta move right.
Oh yeah, we gotta move right. So, I don't know, maybe like here. Then what?
2 pi.
Yeah, right, so we gotta cut this up into quarters. So half of 4 pi is 2 pi, half of that is pi, and of course the third guy here will be 3 pi. So now I'm gonna graph it without the phase shift first. So I'm gonna forget about that pi over 4 shift. And I'm gonna just plot, let's see, -3 cosine of 1/2 x. So it starts at -3 and it goes up from there. Now we have to make room for the phase shift. So there's plenty of space over to the right because we're only going pi over 4, right? So if that's pi, this is pi over 2, and this amount here, there's our pi over 4. So it's just the teeniest amount. There's 5 pi over 4. There's 7 pi over 4. Which one would this be at pi over 4 beyond the 3 pi? Nope. Oh, and you know what? The 2 pi beyond that is actually 9 pi over 4. I got that one wrong. So how many pi over 4s are in 3 pi? 12, and then add 1, and that'll be 13. You're right. 13 is what we want. 13 pi over 4. And pi over 4 beyond 4 pi, what will that be? 17 pi over 4. Because 4 is 16/4, right? So we're just adding 1/4 beyond that. Okay. Now let's plot our new points. Still starts at, oh yes, starts down at the bottom. So I'm just moving each point over, each of our anchor points over by pi over 4. And this looks like this. So here's our graph. this is your fair warning that if I'm asking you to give the phase shift, I want you to give the amount and the direction left or right. Don't just write plus or minus. Actually write out what the direction. I mean, arrow signs are also fine, right? But like, I want something that indicates an actual direction. And that if you are graphing a function, I'm looking to see that you've marked out the x-axis with the appropriate values, including if there's a phase shift that you've marked those appropriate values. It is usually really obvious to me if I'm looking at a graph that somebody just drew by using their calculator, like, because there's a stunning lack of detail, you know, to where things fall when you try to like just draw it from. Yeah, so so make sure that you spend time on these exercises. It will help. You definitely please don't rely on your calculator to do these problems. I think it's a great idea to use your calculator to confirm or to compare what you have with what your calculator does. Make sure that your calculator mode is set to radians, though, in that case. Yeah, okay.
Is that a 17 or a 14?
Oh, this is a 17, yeah. Questions?